Welcome to the Explainer. Today, we're going to jump right into something called the TNB frame. This is a really powerful set of vectors that perfectly describes motion along any curve in 3D space. It's a huge concept in multivariable calculus, so let's break it down. So, let's start with a fun little thought experiment. Picture this. You're on a roller coaster. At any given moment, how would you describe which way you're facing, which way you're turning, and even how you're tilting? It sounds complicated, right? Well, it turns out this is exactly the kind of problem calculus can solve with just incredible precision.
All right, here's what we've got on tap. First, we'll answer the big question. What is the TNB frame? Then, we're going to build it, one vector at a time, starting with T, then N, and finally B. And at the end, we'll see how it all comes together in motion.
Okay, let's get into it. You might hear this called the moving trihedron, which, yeah, sounds pretty complicated. But the idea behind it is actually super intuitive. It's really all about creating a personal frame of reference that just moves right along with you.
Yeah, think of it like this. It's like having your own personal 3D coordinate system, your own little X, Y, and Z axis that's literally attached to you as you move. This little setup is always perfectly aligned with your path, giving us a complete local picture of your motion at any single instant.
All right, first up, we've got the tangent vector. We just call it T. This one's probably the most straightforward of the three. It simply tells us where we're going. So if you're in a car, the T vector is always pointing straight out from your front bumper. Simple as that. It captures your direction, but here's the key thing. It doesn't tell you your speed. That's because it's what we call a unit vector, meaning it always has a length of exactly 1.
Okay, so how do we actually find this T vector with math? The formula is really kind of beautiful. First, you take the derivative of your position vector, r of t. Now that gives you velocity, right? Direction and speed. But t only cares about direction. So what do? We just divide that velocity vector by its own length, its magnitude. This little trick is called normalizing, and it's what guarantees we end up with a vector of length 1.
Let's put this into practice with a classic example you'll see all the time in calculus, a helix. Okay, step 1, find the derivative of the position vector. You can see it right there. Step 2, we calculate the magnitude of that new vector. And thanks to a little help from the Pythagorean identity, sine squared plus cos squared equals 1, it simplifies down really nicely to just the square root of 2. And finally, step 3, we take our derivative vector and divide it by that magnitude. And voila, that's our unit tangent vector, t.
All right, now let's move on to the normal vector, n. You'll see this builds directly on what we just did. So if t tells us where we're going, n is all about telling us how we're turning.
Let's go back to that roller coaster. As you bank into a turn, the normal vector points straight to the inside of that curve. It's basically pointing in the direction you feel those g-forces pulling you. And here's the really important part. It's always at a perfect 90-degree angle to the tangent vector. And check this out, because the formula really shows you how these vectors are all connected. To get n, you take the derivative of the tangent vector, t prime of t, and then you normalize it. Now stop and think about that for a second. What's a derivative? It's a rate of change, right? So the derivative of our times direction vector t is literally telling us how our direction is changing. And what is a change in direction? It's a turn. It's just such a beautiful piece of calculus logic. The bottom line is, you absolutely cannot find n until you've calculated t.
So for our helix, we just follow that same three-step recipe again. First, we take the derivative of the t vector we already found. Second, find the magnitude of that new derivative. And third, we divide the vector by its magnitude. And in this case, you can see how those constant terms, the 1 over root 2, they just beautifully cancel each other out.
And after all that work, what are we left with? This really clean, simple vector for n, negative cos t, negative sine t, and 0. But what does that actually mean in the real world? Okay, here's the key takeaway. Remember, our helix is spiraling around the z-axis. Well, this vector we just found is always pointing from the curve right back toward that central axis. It perfectly captures that inward pull of the spiral's turn. And this is a fundamental rule. N always points toward the center of whatever bend the curve is making. Okay, so we've got our forward direction, t. We've got our turning direction, n. But we live in a 3D world, right? So we need a third vector, one that's perpendicular to both of those to complete our little coordinate system. And that, my friends, is the binormal vector, b. So if t is forward and n is inward, what's b? On our roller coaster, b is the vector that's pointing straight up from the floor of your cart, or maybe straight down, depending on the orientation.
It's perpendicular to both your direction and your turn. Essentially, it defines the bank or the tilt of the track.
Now, B is calculated a little differently. We don't have to take another derivative, which is kind of nice. Instead, we find it by taking the cross product of the two vectors we've already worked so hard to get, t and n. And the order here is super important. It's always t cross n.
So here are the things you really need to remember about the binormal vector. First, just by the definition of a cross product, it's going to be perpendicular to both t and n. Second, since t and n are both unit vectors and they're perpendicular, their cross product, b, is also guaranteed to be a unit vector. It completes our little moving trihedron frame. And it also helps us measure something called torsion, which is basically how much the curve is twisting out of being flat.
Okay, so let's put it all together now. Let's visualize how t, n, and b all work together as one single unit, moving along a path. So just imagine a point moving along that helix. And as it goes, you can picture this three-pronged TNB coordinate system moving and rotating right along with it. It's pretty cool. At every single moment, that frame gives us a perfect, crystal-clear description of the object's orientation in space, its heading, its turn, and its tilt.
And that leaves us with one last thought to chew on. We said B, the binormal vector, describes the tilt or the banking of the curve. Well, the rate of change of B is called torsion. So what could that tell us about our roller coaster ride? Think about it. It would describe the corkscrewing motion, that twisting feeling that pushes you side to side in your seat. And, that's often the very thing that makes a modern ride so incredibly thrilling. Just something to think about.